morning. So we have Solomon Lo from Tongji University in Shanghai, and previously he was at Yokohama National University working with the Ken Tongji. And we talk about minors and non-hamiltonian graphs. Please.
Thank you for the introduction. I'm very glad to talk about some of my research here. So today I'm going to share a joint work with Kendo Ozeki, my previous postdoc supervisor in Yokohama. So the topics is about Hamiltonian graphs and minors. So they are just the standard notions. So Hamiltonian means having a spanning cycles. So this is a book cover about a series of lectures by Tutte. And the figures is drawing a snake want to travel the dodecahedral graph in the Hamiltonian way. So that is the original graph that Hamilton considered. A minor is just the standard notion, the standard minor. For example, in Peterson graphs, it shows that it has a K5 minor as well as a K33 minor. And also, we will use the term minor minimal, which just means that given a graph class, we can order the graphs by the minor relation. And we say that a graph in that class is minor minimal or is a minimal minor, which just means that it is a minimal element with respect to the minor relation. So what do we know about Hamiltonian graphs and minors? Actually, we have a very classical result by Tutte. It says that every 4 connected planar graphs is Hamiltonian. Then, because planarity can be characterized by minors, so this result is basically about minors of non-Hamiltonian graphs. So this result has been extensively studied, and there are several famous extensions. For example, Thomason proved that 4 connected planar graph is not only Hamiltonian, it is Hamiltonian connected, which means that every 2 distinct vertices in the graph, you can join them via a Hamiltonian path. And Thomas and Yu extend Tutte's result to projective planar graphs, which is also an important result. And Kawarabayashi and Ozeki, they combine these 2 properties. They make a unified extension that every 4 connected projective planar graph is Hamiltonian connected. Although we have many extensions of Tutte's results, there is still a largely open conjecture by Greenbaum and independently by Nash-Williams, which says that every 4 connected toroidal graph is Hamiltonian. And so this series of research is about how to extend Tutte's results to other graphs on other surfaces. But today we will focus on the minors. So first, review some basic fact. Kwiatkowski and Wagner, they have the well-known results of them is G, a graph, is non-planar if and only if it contains a K5 or a K33 minor. And further, Wagner proved that if the graph is 3 connected, then G is non-planar if and only if G is isomorphic to K5 or it has a K33 minor. So now, because K5 is Hamiltonian, we can apply Wagner results to show that Tutte's results is equivalent to saying that every 4 connected non-Hamiltonian graph contains a K33 minor. So which is just at the beginning, I said that touch result is about non-hamiltonian and minus. So it is equivalent. And I can also state that every minor minimal four connected non-hamiltonian graph contains a K33 minor, which makes no harm because we just consider the minimal elements with respect to the minor relation. Then we just said that okay, every graph in the class has K33 if only if the minor minimal elements contains a K33 minor. Okay, and there is another result of Wagner which says that every four connected non-planar graph contains a K5 minor. So similarly, we can use such results to conclude that every four connected non-Hamiltonian graph, which must be non-planar, therefore it must have a K5 minor. So we just reviewed two results that in terms of Hamiltonicity and minors, which are every four connected non-Hamiltonian graph contains a K33 minor, and in the same way they contain a K5 minor. We will focus on the first result, the K33 minor. So here is the picture. We have the graph class of four connected non-Hamiltonian graphs. We order them by the minor relation. Then the lower layer are the minor minimals. And Tutte said that, okay, you can always do some contraction or deletion to go down to the K33 minor. But so we can we can look at this figure, and we know that we can somehow improve Tutte's result by finding all minor minimals. If we can find out all the graphs in here, then we can just check. We know there are only finitely many. We just check that, okay, every graph in here will have a K33. Then, therefore, finding all graphs here will be an extension of Tutte's result. Therefore, this the picture in the last slide motivates us that to ask how to characterize the minor minimal four connected non-Hamiltonian graphs. And I think this can be a very, very hard question. So let's consider something else. What if we just put four connectedness to 3 or 2 connectedness? So the question is the same. We want to characterize the minor minimals. Okay, the question 3 is actually very easy. Let's consider if we have a 2 connected non-Hamiltonian graph. We take the largest cycle, then we know it is non-Hamiltonian, therefore we can have a vertex V outside the cycle. Since it's 2 connected, we join from V to the longest cycle by 2 internally disjoint paths, and the 2 vertices at the cycle from these 2 paths are non-adjacent. Otherwise, you can get a longer cycle. Therefore, you can see that we can always have a K23. And these 2 vertices are the parts of size 2. And fortunately, K23 is also a 2 connected non-Hamiltonian graph. Therefore, unlike this picture, in this picture the K33 is outside of the graph class we consider. But in this question, the K23 is inside the graph class. Therefore, we can conclude that there is exactly 1 minor minimal 2 connected non-Hamiltonian graphs, which is K23. So this solves question 3. So how about question 2? The question 2 is just the same question about the three connected case. Interestingly, Guoliding and Emily Marshall, they conjectured in 2018 that the minor minimal three connected non-Hamiltonian graphs are these three graphs. The first one is K3,4, and the third one is the Herschel graph. The middle one is actually combined from these two graphs. Okay, this is the Herschel graph, which is known to be the smallest three connected non-Hamiltonian planar graphs. This is planar. And K3,4 is, of course, non-planar. This one is Q plus. You can see that, okay, this is actually a cube plus one vertex joining these three independent vertices. And you can also say that, okay, actually we just take half of the Herschel, put it here, and half of the K3,4 and put it here. This produce the graph Q plus. So that is the conjecture of Ding and Marshall. Is a conjecture about how to characterize the minor minimal three connected non-Hamiltonian graphs. So we can first check whether this conjecture holds for the Peterson graph, and it is. You can see that the Peterson graph is three connected non-Hamiltonian, and it contains K3,4 as a minor. The part of size 3 is indicated by the red colors, and the 4 parts is by the yellow colors. So let's review some other related results first. Because Tutte said that every 4 connected non-Hamiltonian graph has a K3,3 minor, it is a follow-up question to ask, okay, what if we consider only 3 connected non-Hamiltonian graphs? Ellingham, Marshall, Ozeki, and Tutte, they proved that 3 connected non-Hamiltonian graphs may not always have a K3,3 minor. But if it does not have a K3,3 minor, it will have a K2,5 minor. You can also rephrase the results as they did. Every 3 connected non-Hamiltonian planar graphs has a K2,5 minor. Then they discuss whether K2,5 can be improved to be K2,6. And the answer is no, because the Herschel graph has no K2,6 minor, which can be proved by structural analysis. Then, although we cannot assure a K2,6 minor, but Ellingham, Marshall, Ozeki, Royal, and Tutte, they try to use some computer search to see how many such graphs exist. They then notice that there are actually not much. They do the computer search up to 16 vertices. I think it's 17 vertices, but anyway, they conjecture that every 3 connected non-Hamiltonian graphs on 16 vertices that has neither a K3,3 minor nor a K2,6 minor is one of a list of graphs which consists of 40 graphs. Here is the pictures. The conjecture is, if you have a graph which is 3 connected and non-Hamiltonian, then also it has no K3,3 minor and K2,6 minor, then they look like one of these figures. It is basically.
How big is the biggest one? Like out of 40, how many vertices?
It is depend on the number of vertices. For example, if you consider the number of 16 vertices, then there are 40 such graphs. If you consider there are 17, there are also 40. Because the differences are just what dash edges you choose. And up to symmetry, they're always the same. When the number of vertices increase, the difference are only the size of this fan. So, yep, they want to characterize the exceptional cases.
Oh, I see.
And between K25 and K26, we have K115. Actually, Ellingham, Gaslovis, O'Connell, and Royal, they proved that every 3 connected non-Hamiltonian graphs, except for the Herschel graph, students' thesis and not yet published. So Ding and Marshall conjecture that every 3 connected non-Hamiltonian graph has a minor of one of the 3 graphs. And actually, I can also briefly explain why these 3 graphs are non-Hamiltonian. So we can directly track that it's 3 connected, but why they are non-Hamiltonian? The reason is because each of them is bipartite and has an odd number of vertices. Every of them has an odd number of vertices. Therefore, they cannot be Hamiltonian. Every Hamiltonian bipartite graph must have an even number of vertices because you go alternatively from one color to another color. So these 3 graphs are quite interesting. And let's go back to the conjecture. In the same paper, when they proposed the conjecture, they proved that this conjecture holds for planar triangulations. So, which means that every non-Hamiltonian planar triangulations, which must be 3 connected, which must have a minor of the Herschel graph. Because K34 and Q plus are non-planar. And the proof comprised of a computer proof. They actually characterize all such planar triangulations. Then last year, Ozeki and I proved that this conjecture holds for planar graphs. And I think it is interesting to note that our proof does not use any computer. And we also apply our results to prove the Ellingham et al.'s conjecture. I think it's not so surprising because the conjecture is, you can see that the graph they characterize it looks like a Herschel graph. So as long as we can have this result, we can apply this to prove their conjecture. There are 2 more consequences. The first is we talk about that the Ellingham et al. They proved that every 3 connected non-Hamiltonian planar graphs has a K25 minor. Actually, this is also a consequence of our result because the Herschel graph has a K25 minor. Another consequence is since the Herschel graph is the minor minimal 3 connected non-Hamiltonian planar graphs, which means that it is also the smallest 3 connected non-Hamiltonian planar graph. And this result is known for many decades ago. Then afterwards, I continued to study the conjecture, and I proved that the conjecture holds in general. which means that, let's repeat the statement, which says every 3 connected non-Hamiltonian graphs has a minor of K34, Q plus, or the Herschel graph. So here is the picture about the question 2. In this class of 3 connected non-Hamiltonian graphs, the minor minimals consist of exactly these 3 graphs. And there are also other research motivated by test result. For example, we know that in the statement of test results, we cannot replace 4 connected by 3 connected. But if we do so, we can still have a long cycle in the sense that we can have a cycle of length which is of the order of n to the power of log 2 with base 3, which is something like 0.6 or something. But it is not a linear cycle length. And Chen Yu and Zhang, they extend their results for a general K3T minus. They prove that there is a constant beta such that for any integer t at least 3, every 3 connected graphs without K3T minus has a cycle of length n to the exponent beta. And there is a hidden constant in this spec omega, which depends on t, but not, it's dependent on t, but the exponent beta is independent of t. Then Chen Yu Zhang, they conjecture that, okay, if we leave up the connectivity to 4 connected, then we can have a linear length. The statement is for any integer t, at least 4, there is a constant depends on t, such that every 4 connected graph without K3T minor has a linear length, which means alpha times n. So as a special case, and actually in the same paper that Deng and Marshall proposed the conjecture we just talked about, they asked whether every 4 connected non-Hamiltonian graph has a K34 minor. And with similar techniques, I proved that the question is true. Which means that every 4 connected non-Hamiltonian graphs, you can do some deletion construction and to reach the K34. So here is the picture. Previously, we know that every 4 connected non-Hamiltonian graphs can go down to the K33. And our results improve these results to K34. But still K34 is outside the graph class. So it's still just a small step. So let's discuss some proof. And I would like to talk about the proof about the result that every 4 connected non-Hamiltonian graph has a K34 minor. So how to prove this? We have a 4 connected non-Hamiltonian graph. We want to show that it must has a minor of K34. So first of all, since this graph is 4 connected and non-Hamiltonian, by the results of Thomas and Yu, we mentioned in a long time ago that we know that this graph is not projective planar, which means that we cannot embed it in the projective plane. Then it is a well-known result of Arch-Diacon that if the graph is not projective planar, it must contain some certain minors. It is a Wagner type theorem. The Wagner theorem is talk about the non-planar graph and Ashe-Diacon's theorem is talk about the non-projective planar graphs. Then if we additionally know that this graph is three-connected, then Robertson, Simon, and Thomas, they proved that actually the minor is not only from the Ashe-Diacon's list, but it is a three-connected graph from the Ashe-Diacon list. So here is the list of Ashe-Diacon, and here is only the three connected ones. So we can see that there are 23 graphs, and most of them already has a K34 minor. Many of them. There are only 4 exceptions. This one, this, and this. Only these 4 graphs has no K34. Therefore, we can conclude that our 4 connected non-Hamiltonian graphs must contain a minor of this, or this as a minor. This is our step 3. We reached the conclusion that G contains a minor of one of these 4 graphs. Then what we need to do is this part is our core part of the proof. We can actually show that G has not only a minor of one of these 3 graphs, but actually G has either a spanning subdivision of this graph E20 or F4. So we need to do a lot of case analysis to reach this conclusion. But once we have this conclusion, then it is much better, because if we know such a spanning subdivision, and our goal is to reach the contradiction that this graph G has a Hamilton cycle, so this spanning subdivision will be very helpful. And it is interesting to note that in this step 4, we do not need to consider anything about Hamiltonicity. We only need to apply that, okay, G is 4 connected, and G has one of these 4 graphs as a minor, then we can show that, okay, actually we will have this. Now, of course, we need to use the condition that G has no K34 minor. Then after obtaining this subdivision, spanning subdivision, we can find a Hamilton cycle, and this is our final contradiction. So in the following, I will talk more about this structure analysis. So how to do this? There is a very useful tool called seminal splitter theorem. The seminal splitter theorem, which says that if we have a 3 connected graphs, and then these 3 connected graphs has a contain a minor of another 3 connected graphs. So you can imagine that, okay, I start from a bigger graphs, I do some deletion contraction, and it goes smaller until I get a minor of another 3 connected graphs. So you may wonder that, okay, these paths of operations, would it go out of the graph class of 3 connected graphs? And Simon told us that we can always find a path which stay inside the class of 3 connected graphs. Which technically the statement is, if G contain H as a minor, and G and H are both simple 3 connected, and H is not a wheel, then G has a minor of another graph H prime, such that H prime is obtained from H by adding an edge or splitting a vertex. And H prime is also 3 connected. Here we need to emphasize that splitting a vertex into 2 new vertices then these two new vertices has no common neighbor, which means that we can only split a vertex of degree at least 4. So let's see a very quick example. For example, we know that the theorem of Wagner says the minimum minus of non-planar graphs are K5 and K33. We can actually apply seminal splitter theorem to show that if we consider only 3 connected non-planar graphs on at least 6 vertices, then the only minimum minor is K33. So let's say we have a 3 connected non-planar graphs. By Wagner theorem, it says either K5 or K33 as a minor. If it is K33, we are done. So which means that we have a K5 minor of our graphs. But our graph is not K5. It contains K5 as a minor, but it is not K5. So by seminal splitter theorem, you can obtain a larger minor by adding an edge between 2 non-adjacent vertices, or you split a vertex. But now K5, you has no way to add an edge to 2 non-adjacent vertices, which means that we has this graph as a minor, which is obtained from the K5 by splitting one vertex, and there is only one way to do that because of the symmetry of K5. So, but this graph contains K33 as a minor. Therefore, we conclude that every 3 connected non-planar graphs on at least 6 vertices has K33 as a minor. So it is a application of seminal splitter theorem. And of course, you can also argue elementary why every 3 connected non-planar graphs on at least 6 vertices has a K33 minor. So what we do in our structural analysis is very similar to what we have just seen. If we can show this proposition. Let G be a 3 connected graph contains a minor of D17, which is this graph, D17. You can see that is one K4 and another K4 joined by matching. And we also have the condition that the graph has more vertices than D17. Then we conclude that G has a minor of K34 or E20. E20 is this graph, which is similar. We have a K4 up, and at the bottom we have a K23, and they are matched by matching, but one 3-valent vertex of the K23 are not covered by the matching. So now we start with this graph, and we can show that using seminal splitter theorem, since the graph has more vertices than the D17, which means that G contains a larger minor, which is obtained from D17 by at least splitting one vertex. We can add some edges, and we don't know. We can also do not add any edges, but we need to split at least one vertex of D17. So here are all the possibilities. That I need a graph to obtain from D17 by split at least one vertex, and then I need to add some edges or none to keep the graph 3 connected. So the first and the fourth graphs contains a K34 minor, and the other graphs actually contain E20 as a spanning subgraph. Therefore, we can conclude that if G is a 3-connected graph that contains a minor of D17 and G has more vertices than D17, then G has a minor of K34 or E20. Here I present another example that we do in our structure analysis. We consider a 4-connected graph G. If G contains a minor of E22, then it also contains a minor of K34. That is just our setting. We consider G is 4-connected, and what happens if it has E22, and then actually it must contain K34 minus. And this graph is the E22. You can also see another drawing of the same graph, which is a cube, and we add a vertex and join it to 4 independent vertices of the cube. So if G contains a minor of some graph, we know that we can always find a model in the following sense, which is if the graph is cubic, if G contains a minor of a cubic graph, we know that it actually contains a subdivision of the cubic graphs, right? But our graph is not cubic, but it has some cubic vertex and some quartic vertexes. So actually these degree 4 vertices will correspond to a single vertex or a path. But okay, G has a minor of H. If G has a minor of H, then a degree 3 vertex will just correspond to a degree 3 vertex, and the edge will be some path, just like a subdivisions. And if it is a degree 4 vertex, it will correspond to a single vertex or a path. And if it corresponds to a path, we know that each of the vertices is exactly incident to 2 paths correspond to these 4 edges. And if this happens, we call that, okay, it has a split. And we don't care about the additional vertices, the additional vertex in the middle. We don't care whether it is split or not. We only care about the other 4 degree 4 vertices, whether they are split. Then we can go into the case analysis. The first case is, okay, G contains the graph E22 such that we have 2 or more splits. We have 2 or more splits, which means that, okay, these, and these 4 vertices, among them, 2 of them are splits. 2 of them are splits. Then, by the symmetry, there are only 4 cases, which are listed here. You can see that, for example, these vertex are split into this path, and these vertex are split into this path. So, for example, if this configuration of splits happens, okay, we immediately has a K34 minor. And by symmetry, there are other 3 kind of situations, and all those situations, we can conclude that, okay, we have a K34 minus. Therefore, the case 1 is finished. The second case is E22 has exactly one split. It is by the same way. Actually, if it has exactly one split, then the split is up to symmetry unique. So you can see that in this graph, we split this, and we split this, we split this. Then the interesting thing is, okay, when this is split, this vertex split to here, the interesting thing is this and these three vertices are not split. When they are not split, then okay, don't look at this edge. Then this vertex must go out because this is four connected. We delete these three vertices. This part must join to the outside. So we have this situation, and this situation, and also this situation. And we can see that they are all possibilities, and every possibilities use a minor of K34. Therefore, case 2 are also done. So the last case is the graph G has no split. And when it has no split, which means that it is just a subdivision of E22, again, we can argue that, okay, there are some set of three vertices, we can delete it, but the graph is four connected, therefore the part the two paths must be joined by some paths. So there are three possibilities, and each of them again has a minor of K34. Therefore, we exhausted all the possibilities, and we can conclude that if G is a four connected graph and it has a minor of E22, then it also has a minor of K34. So we just discussed some proofs, and now let's talk about some remaining open problems. So I think the most important one is our question 1, how to characterize minor minimum four connected non-hamiltonian graphs. Actually, I do not have much idea. I have actually no clues. But if we look at what we have for the 2 and 3 connected cases, we have K23, K34, Q plus, and the Herschel graph. They have one common pattern, that they are bipartite, and one part has exactly one more vertices than another part. And that part with one more vertices, they have the degree equal to the k. I mean, if it's k connected. For example, it's 3 connected, you can see that, okay, in the yellow part, every vertices has degree 3. And also for the Q plus, you can see that these 5 vertices, each of them has degree 3. And this is also holds for the Herschel graph. So we conjecture that maybe it also holds for the 4 connected case. Another open problem is we just mentioned that we solve a special case of the Chen-Yu-Zhang conjecture, but the general conjecture is still open. It says that every 4 connected graphs, if it has no K3T minus, then it has a linear circle. There are some other related open problems. For example, how to characterize minor minimum 4 connected non-projective planar graphs, which is suggested by Ding and Iverson. They prove for the internally 4 connected. And actually in our proof, we use the result that we use the results by Robertson, Seymour, Thomas on characterizing minor minimum 3 connected non-projective planar graphs. So I think it's closely related to our main problem. The other 2 open problems are also characterizations. One is to characterize graphs without K34 minus. We know that this graph class containing all planar graphs, and Mahari and Sliati, they characterize these graphs when it is embedded in the projective plane. So in the rest, we only need to consider graphs which has no K34 minus and which are non-projective planar. Finally, there is a question by Marshall. She asked to characterize graphs without K25 minus. And the results for K24 is known by Ellingham, and it's quite interesting to note that this result is known and is not known until 2016. But in 2011, Mahari and Sliati already began to study the K34 minus 3 graphs. So it's my talk. Thank you.
Thank you. Any questions?
Do we have an idea what the lowest genus 4 connected graph, or what is the lowest genus 4 connected graph we know that's not Hamiltonian? So what's the worst counterexample?
Okay.
So we don't know one for.
I think you mean the conjecture of Greenbaum and Nash-Williams, right? Actually, the how to say. The only unknown situation is the toroidal and the Klein-Bottle.
I was going to ask Klein-Bottle. Okay.
Yes, and Klein-Bottle is also a conjecture. It's also open.
But for everything above this, we know that it's non-Hamiltonian.
Yes, for higher genus, it's known to be non-Hamiltonian exist.
Is it because of no? So I was thinking some wrong example.
This result by Robertson and Seymour that says that you can, if you're looking at 3 connected graphs, you stay within the 3 connected graphs if you go through the minor relation. Does this also hold for all other surfaces?
We don't know.
You don't know?
What do you mean? If you
So you use the result by Robertson and Seymour that said
yes.
if I'm 3 connected and I have a minor archdeacon's list, I have a 3 connected minor archdeacon's list. Is the same thing true for Klein-Bottle and the torus?
I mean, you can always, for example, you consider 3 connected graphs that cannot be embedded in the torus.
Mm-hmm.
You can always sort them by the minor relations.
Mm-hmm.
Then there is always the minor minimal such graphs.
Mm-hmm.
So that always exists.
Yeah, they are, but they're not minor minimal for the minor relation in total, right? You could still have a 2 connected counterexample that you can embed. But this, even for 3 connected graphs, this is completely unclear how to do this for toroid, right?
Yes.
Yeah. But this would help, right? This might make the proof easier, because if you knew these. I know, I guess you would also have to solve this Greenbaum-Nash-Williams conjecture to say that, okay, I contain something from archdeacon's list and also from the toroid list, and I would need to know the toroid list, and that Nash-Williams and Greenbaum is true. I'm just thinking of how to simplify this proof, like get the cases.
For example, if you can find out all the minor minimal graphs, that cannot be embedded in torus, or can be embedded in the torus.
Cannot be.
But then it is not the graphs that the Greenbaum-Nash-Williams consider. They consider graphs that can be embedded in the torus.
Yeah, sure. I'm trying to figure out what it would need to simplify the number of cases you have to consider.
For the Greenbaum-Nash-Williams?
No, for your proof.
For my proofs.
I'm trying to figure out, like, can we somehow reduce this to the intersection of toroid and
Yes, I think if we can have such strong results, we
Yeah.
can decrease many analysis.
Hmm.
Yes, that's true.
So when you use, can I ask one? Yeah, when you use splitter theorem,
Yes.
like in the worst case, how many steps do you split a vertex to find the one you want? Like, were you always lucky that one split already finds you what you want, or?
For the D17, we are lucky. For the D17, we are lucky. Actually, at the beginning, we have 4 graphs, right?
Yeah.
The D17 is very easy, very lucky.
Mm-hmm.
We just go to E22 or K34, and for the it's always go to the E20 or K34, and for the E22, we are also sort of lucky, but we actually do not directly use the CMOS splitter because it's for free connected graphs.
Mm-hmm.
So strictly speaking, we use the principle of the splitter theorem.
Okay.
E22 are also lucky. Then for E20 and F4, we show that it is spanning subdivisions, which means that first, no splits are allowed. Second, no bridges are allowed. So we just keep doing case study.
Okay. How long is the proof?
I think for the core analysis, like 7 to 8 pages. So
Any other questions? So for that, let's thank the speaker.